So here we have a third set of bonding questions. They're all multiple choice. They're all from AQA past papers for A-level chemistry. So my suggestion is that you pause the question, have a go at it, and then review. And when you've done that, move on to the next one. Okay, let's start with the first one. And if you've worked through all three of the videos here, you will see there's a huge amount of commonality in the sort of questions that can come up, certainly in the context of multiple choice. In this case, we want to know which compound has the highest boiling point. We've got an aldehyde, an alcohol, an alkene, and a haloalkane. So if we draw those out, and we can see on the right-hand side all of those structures, and we've put the key parts of those structures in as well. So we've got the double bond showing in the alkane, we've got the OH in the alcohol, the COH in the aldehyde. And whenever there's a question about highest boiling point, you're almost certainly going to be comparing intermolecular forces against each other. And in this case, we have got hydrogen bonding evident in the alcohol, and we don't have hydrogen bonding in any of the others. C is only van der Waals forces. A and D have permanent dipole, permanent dipole. So for that reason, the correct answer is B. So in terms of bonding, it's about recognizing what type of bonding is present within a range of different substances. So let's take a look through these and see which ones we can easily dismiss. Well, graphite is giant covalent. It's one of the two allotropes of carbon that really the whole of the giant covalent topic hinges on. So it can't be that one. Sodium chloride is ionic, metal bonded to a non-metal. We are going to think of as an ionic compound, certainly not giant covalent. And diamond, as I've already touched on with graphite, is another very, very commonly discussed giant covalent compound. Now that leaves us with iodine, which is simple molecular. Now there's an interesting bit of chemistry here that the I2 molecules are held together in a crystal lattice, but they're held together by van der Waals forces. That's what helps us to understand why iodine will sublime. It will go from a solid to a gas at such a low temperature, because actually the forces holding that crystal together are weak. And I did talk about variations on a theme. This one, which compound has the highest boiling point? So once again, we are looking for the intermolecular forces present in each example, and then deciding which one of them is strongest. So we've got van der Waals. Stronger than that is permanent dipole, and the strongest is hydrogen bonding. Now, as is commonly the case, there is an alcohol here, and that alcohol has hydrogen bonding. It's got the OH bond. None of the others show hydrogen bonding. So the correct answer is A. This is a straightforward definition question. Obviously, for it to be that straightforward, you have got to be confident with your definitions. So let's take a look through and see if we can narrow it down at all. Well, it is a pair of electrons. A dative covalent bond is one pair of electrons. So we can immediately disregard C and D. But from there, we then have to consider what's different about a dative covalent bond. What sets it out apart from normal covalent bonds? And it is the idea that one of the atoms involved in the bond has donated both electrons. So the correct answer is B. Another very common question type. So what we're looking for here are bond angles, shapes of molecules. Which of these will have a trigonal planar structure? Now you could draw them all out, and you've seen examples of that on previous videos, but there is another way that we can consider this. If we take a look at what's in the centre of the atom or ion, we've got phosphorus in A, which is in group 5. Boron in B is in group 3. The oxygen is in the centre on C, and that's in group 6. And carbon is in group 4. So from there, I am looking for, knowing that trigonal planar is 3 bonding pairs, that group 3 is more likely to give me that. So that's going to take me to BCl3, 120 degree bond angle. Group 5, if I form 3 bonds, that means there's a lone pair on the P. That means based on tetrahedral. So you can draw them all out, but you can find shortcuts through as you get more confident with them. So again, with this, you might want to take the time to draw out the structures so you can be really, really clear about what the bond type is going to be. So if I do the dot cross structure of ammonia, as we can see here, we know that nitrogen has got a lone pair on the N. BF3, well, we've just spoken about the fact on the previous question that boron is in group 3. So we have 3 bonding pairs and we have no lone pairs. What that does mean is we have a vacant orbital on the B. So we can form a coordinate bond where both of the electrons are provided by the N. So cycling back around now to intermolecular forces, this hinges on you remembering that hydrogen bonding will exist in a compound where an H is bonded directly to an N, an O, or an F. And in hydrogen fluoride, it definitely has that. The H is bonded to an F. In ammonia, the N is bonded to H's, so there's that direct link. In ethanoic acid, we have an OH, so the O is bonded to the H. All 3 of these so far do show hydrogen bonding. CHF3 does have Fs in there, but the Fs are not directly bonded to an H. So for that reason, the correct answer is D. So this is a question linked to ionic bonding. It's related to ionic formulae and the formulae of ionic compounds. So we need to do quite a lot with this. First of all, we need to know that a nitrate 5 ion is NO3 minus. And we can see here if each oxygen is -2 and the overall charge is -1, the N is +5, which gives us the overall charge of -1 when combined with the oxygens. I'm now going to put these onto a seesaw. There's different ways of doing this. I quite like this as a visual representation. So I've put my NO3 minus on. I also know that calcium is +2 because calcium is in group 2, so the ions it forms are +2. So my seesaw is not currently balanced. I need to add more on the left or the right until my charges cancel out to 0 because there is no charge on calcium nitrate. So I need to add another -1 on here. So I've got 1 calcium and I've got 2 nitrates. Now I need the brackets there, so the answer is B. So the most important thing here is understanding what we mean when we're talking about macromolecules. And macromolecular is related to giant covalent. So when I break that down a little bit further, copper is metallic. It's a metal, we know that one, so we can immediately dismiss it. P4O10 is molecular covalent. That's certainly not giant covalent. There would be intermolecular forces between P4O10 molecules. And magnesium oxide, metal and non-metal, is ionic. Now, silicon dioxide does come up quite commonly in exam papers and will almost certainly have been covered in the content of your course. Silicon dioxide has a very similar tetrahedral structure to diamond, and so there are often questions that will relate it to diamond and ask you to answer questions about its giant covalent properties. But for the purposes of this question, we're simply identifying that that one is giant covalent. So the correct answer is B. So on this, it's a matter of working through and seeing which does not involve the donation of an electron pair. And if we take a look, we'll go through step by step. In A, this is clearly forming a dative covalent bond. The N is donating both electrons to that dative covalent bond. So definitely is not the answer because it does involve that electron pair. Now B is also a dative covalent bond. AlCl3, my Cl- provides both of the electrons that form the final fourth AlCl bond. Part C takes us into organic territory. Now, you would have to remember that Cn- has a lone pair. Because it has that lone pair and it can act as an electron pair donor, which is the definition of nucleophile, we know that C involves the electron pair and is therefore not the correct answer. And so we're left with what's essentially a displacement reaction between halogens, no electron pairs involved, and so the correct answer is D. Back now to shapes of molecules. We want to know specifically the bond angle alpha, so between the two F's on the left-hand side. First thing to do is identify what shape it's based on. There are 5 pairs of electrons in total, so it's based on trigonal bipyramidal. Bond angle for which is 120 degrees and 90 degrees. Now, we can therefore immediately dismiss B and D because they are so far away and no number of lone pairs is going to cause that much reduction in bond angles. So what we can then do is think about where within the structure the alpha actually fits. And if you think of trigonal bipyramidal as being a trigonal planar with one bond going up above it and one bond going down below, the alpha is within the trigonal planar component of it. So we know that that one's going to be 120 degrees rather than 90. But we also know that lone pairs cause some disruption to the bond angles. They cause distortion. They are going to push the bonding pairs closer together and therefore reduce the bond angle. Generally, we would say by around 2.5 degrees. Now, the closest we have to that is a 2-degree reduction from 120 to 118. The correct answer is A. So which of these is not influenced by a lone pair of electrons? If we start to piece together what we have here, we've got oxygen in group 6, we've got fluorine in group 7, we've got boron in group 3, and we've got nitrogen in group 5. Now, I am going to take a look at that and think which of those does the shape relate to the number of bonds surrounding it. So, for example, NF3, I've got 3 bonding pairs, but nitrogen's in group 5, so I have a lone pair as well. So that's going to be based on tetrahedral. It will be trigonal pyramidal. But if I move up to C, where I've got BF3, boron is in group 3. Each of its outer electrons goes into one bonding pair. So I have 3 bonding pairs and I have no lone pairs left, as we can see here. And for that reason, the correct answer is C.